This is Mr. Sindel filling in for the sick Miss Anderson, and I'm going to go through the practice final for Algebra 1, questions numbers 1 through 25. So here are the first 4 questions, and really the first 6 questions have a few basic rules that I want to go over really quickly. So these basic rules, if I do anything in red, please add this to your note sheet. You are allowed to have a note sheet for the final. It's just a freebie to get these questions. So this category, I guess, is going to be called multiplying. And you don't need to have the title here. I'm just giving you a title just in case you need to refer back to it. Monomials. And monomials is just a fancy way of saying stuff like 7x squared, something like that. Things that don't have any pluses in it. There's no plus or minus. Okay, so when you multiply monomials, there are basically 2 things that you have to keep track of. The numbers, also known as the constants, and the variables, also known as the letters. Okay, so the numbers. What do you do with the numbers? You just multiply all the numbers. Multiply. And then the letters, you just need to count. Count the number, how many there are. So I'll do a quick example really quick. So if I have 3x, I guess I can do an example underneath. That makes more sense. So an example, if I have 3x squared times negative 2x to the 3. Okay, so the numbers. There's a number right there. I'm doing this part right here, the numbers. There's a number 3 and there's a number negative 2. Notice that I do include this negative sign in with the negative 2. So I need to multiply 3 and negative 2, and that gives me a negative 6. So I just multiply the numbers. Okay, now let's deal with these letters, the variables. So the letters, I can do that in black here. These are the letters, I would consider them. And the power here represents how many there are. X squared is really x times x. It's counting how many times I'm multiplying. I'm multiplying once and twice, so that's why there's a 2 here. So how many x's are there here? There's 2. How many x's are there here? 3. 2 plus 3, there are a total of 5 x's. The way that we write that is x to the power of 5, and that's our final answer. So just make sure that you multiply the numbers, and then you count the letters, and then make sure you're paying attention to the exponents here. A few things that we also need to keep track of is what happens when there's blanks. So if I have x, this is the same thing as 1x to the power of 1. You can always add a 1 in front of anything, and if there's no power, it's assumed to be 1. The count is 1. And there's other things too where I think you probably already know this, where if I have x to the power of 0, how many x's are there? There's no x's. This is the same thing as 1. Just multiply everything by 1. All right, let's actually get to these problems now. So again, I'm going to first deal with the numbers. So the numbers I'm going to do in blue here. So I have a negative 3. Remember, I include this negative. I have a negative 2, and I have a negative 3. I need to multiply all these together. So I can even show my work. I'm not going to show my work this in depth for the rest of the problems, but I think it's good for number 1. I'm taking negative 3, I'm multiplying negative 3 by negative 2, multiplying that by negative 3. Okay, so let's deal with the signs later. Let's just do 3 times 2 times 3. 3 times 2, 6. 6 times 3 is 18. So this thing turns into 18, and now we'll deal with the sign. Negative times a negative, these two form a positive. And then a positive times a negative, this is a negative right here, positive times a negative is a negative, so our final answer is a negative 18. We just dealt with all the numbers. Now we're going to deal with the variables, the letters. So I have v. If there's no power, you assume it's the power of 1. This is a v to the power of 0, v to the power of 2. Let's count up how many v's there were. There's 1 plus 0, which is just 1. And then 1 plus 2 is 3, so there's a total of 3 v's. So we say v to the power of 3. And I think I can write that a little bit down here so I have more room. So this is a negative 18 v to the power of 3. And then I'm going to box my final answer. And I can rewrite what was up here. Perfect. Let's do the same thing for number 2. So first, I'm going to deal with all the numbers. I have a 5, and I have an invisible 1. I don't really have to worry about him, because 5 times 1 is just 5. So dealing with all the numbers gives me 5. Perfect. Moving on to the letters. And I guess I can use black just like I did in my notes. So I have 2, and then how many do I have here? If there's nothing here, you assume it's 1. So how many n's do I have? I have 2 there and 1 there, and you just add them, a total of 3. I'm counting how many n's. There are 3 n's. So I say n to the power of 3. That's my final answer. Box it. Moving down here to number 3. Again, deal with the numbers first, then the letters, then the variables. The technical term is constant instead of number. So the constant is -2 here. The constant is -5. So I'm going to have a -2 times a -5. -2 times -5 is a positive 10. A negative times a negative is a positive. 2 times 5 is a 10. Now let's count the v's. I have v to the power of blank. Blank turns into a 1. So I have 1 v there, no v's there. This is 0 v's. So 1 plus 0 is 1. So it's v to the power of 1. So I can either say v to the power of 1, I'll get full points by saying that, or I can say this is the same thing as just 10v. This is the preferred form right here, but you will get full points if you say 10v to the power of 1. That is mathematically correct. Let's move on to number 4. Again, we're going to deal with the numbers first. So I have 3, and I have a -2. Remember to include that negative sign in there. This is going to be 3 times 2, which is a 6, but we didn't include the negative. It's a positive times a negative, which is a -6. Perfect. Now we're going to deal with all the letters, the variables. A to the power of 4. This means that there are 4 a's there. There are 2 a's there for a total of 6 a's. So we need to write a to the power of 6. This is just counting the number of variables here. Box our final answer. Let's move on to number 5. So in this problem, we have 2 different variables, 2 different letters. We have a y and an x. We have to keep track of which one is which. We can't mix them. We can't mix our peas and our corn. We have to keep them separate. So we'll count them individually, but the same process as before. We're going to first multiply all of the numbers, and then we'll deal with the letters. So the numbers, let's go ahead and find those. There's an invisible 1 here, but we don't care about that because 1 times whatever is whatever. So we don't even need to put the invisible 1 there. I have a 4 here and a 4 here. There's no negative signs to include, so I just need to do 4 times 4. 4 times 4 is 16. Perfect. Okay, so now I'm going to count all of the, I can either choose x's or y's, it doesn't matter. I'm going to just arbitrarily choose y because I see y first. Okay, this is y to the power of what? Is it y to the power of 0? It's not. This is x to the power of 0. This is y to the power of an invisible 1. If there's nothing there, you always assume it's a 1. Each of these letters needs an exponent. If there's no exponent, assume it's 1. Okay, so there's 1 there. Are there any other y's? Oh, there's an exponent there, a -1. Perfect. Okay, so I need to count how many there are. There's a positive 1 there and a -1 there. So it's a 1 plus a -1. 1 plus a -1. That's the same thing as 1 minus 1. 1 minus 1 is 0, so there are a total of 0 y's. Well, if there are 0 y's, I don't need to put a y. Or, alternatively, you could say, well, okay, it's going to be y to the 0, Mr. Sindel. And I will tell you that is great, but it needs to be simplified. Anything to the power of 0, and this is a rule that we should know, anything to the power of 0 is 1, and then 1 times 16 is just 16, so it disappears regardless. There are 0 y's, don't put a y. Let's move on to the x's. So x's I'm going to do in a different color. I'm going to do it in green. Hopefully we can see this color. Hopefully. I don't know if the projector is equipped to handle that color. So x to the power of 0. There are 0 x's. Okay, well, I basically say, okay, I don't really need to worry about him, but there are 0 x's, another -2 x's, and I don't need to worry about x's there either. So between 0 and -2, that adds up to -2. There are a total of -2 x's. So there are a total of -2 of these x's, x to the power of -2. That's my final answer. Box it. And I just want to reread the instructions back here. I need to simplify. Oh, okay, read here. The answer should only contain positive exponents. But look at our answer here. Our answer has negative exponents. Uh-oh, that's a problem. So let's undo this. That's not box. We need to get rid of this negative exponent. And this is where it helps to know a rule. And I'm going to do this rule in red. You should add this to your notes. So this is just called negative exponent rule, I guess. Negative. I'm just going to abbreviate like that. Negative exponent. So what happens if I have something like x to the power of -a? We'll keep it general, and then I'll do an example. This is the formal rule, though. X to the power of -a is equal to 1 over x to the power of a. Well, that's great. How do I memorize that, Mr. Sindel? The way that I do this is I change this into x to the power of -a over 1. You're allowed to divide anything by 1 because it's just the same as it was. So what I'm going to do is I divide it by 1, and then what I do is I flip these two. So it's 1 over x to the power of negative a, and then instead of having a negative a, you just make it a positive. So flip it, and then change it to a positive. Let's do a quick example to make sure we understand this. Quick example. So if I have 2 to the power of negative 3, that's going to equal to, okay, so first, I need to make sure that this is a fraction. If it's a fraction, then I'm ready to go. Okay, now it's a fraction. Now I'm going to flip the top and the bottom. I'm going to flip the numerator to the denominator and the denominator to the numerator. So this is now 1 on the top, and on the bottom I have this, go back to blue, there we go. I have this 2 to the power of, it was negative 3, but now it's a positive 3 because I flipped it. And then I can simplify this a little bit more because 2 to the power of 3 is 2 times 2 times 2, which is 8. So this is 1 over 8. One more quick example, you might see this type of form as well. You might have 1/2 to the power of negative 2. Okay, what do I do in this case? Well, I already have a fraction. I didn't have a fraction, so I had to make a fraction back here, but I already have a fraction, so this is even easier. Okay, it's ready to be flipped. Go ahead and flip the top and the bottom. The bottom was 2, so it comes up to the top. The top was 1, it goes to the bottom. And the outside, because this is not attached to the top or the bottom, it's just on the outside, leave it on the outside. It changes from a negative 2 to a positive 2. Those are the two types of negative exponents that you might see. Let's go back to the problem and see how to apply that. So in this problem, I had x to the negative 2. So let's change this, and remember, this negative 2 right here only applies to this x. It does not apply to the 16. So when I make my fraction will only be with the x over 1. I'm not going to write this whole thing over 1. That would be, it would be mathematically correct, but it's going to confuse us. So only attach it to the exponent. Only attach it to the variable, rather. Okay, now it's set up. Now I can flip the top and the bottom just with this x. The 16 is going to stay the same. So I'm going to rewrite that 16, and now I'm going to change the x. So it's now x squared on the bottom, and on the top I have 1. Remember, it turned into a positive once I flipped it. Now I have the correct answer. And I can simplify that a little bit if I wanted to. This is still 16 times 1 over x squared. You'll get full points once you get to this answer, but this can be simplified a little bit to get to 16 over x squared. The reason for this is it's 16 over 1, and it's going to be multiplication of fractions. 16 times 1, you multiply straight through. 16 times 1 is 16. 1 times x squared is x squared, and that is my final answer. A lot that I talked about in this problem. Let's apply the same thing to number 6. And I don't think we'll need to flip anything. I'm just kind of looking ahead here. Okay, same process as before. Deal with the numbers first. There's a number there. There's no more numbers. Everything else was in the exponent. I'm done. If I just have a 2, I'm just done with 2. Now I need to count all of the x's and the y's. Let's do x's first. I see x first. How many x's do I have? I have 3 there. No more x's. Oh, so I'm done. I have 3 x's. So I say, I should have done that with black, by the way. I'll recircle that with black. So this is going to be x to the power of 3. Perfect. Now let's deal with the y's. How many y's do I have? Well, I have 2 y's there. And I should do this with a different color now to not mix it up with the x's. I have 2 y's there, and I have negative 2 y's there. Well, 2 plus a negative 2 is the same thing as 2 minus 2, and 2 minus 2 is 0. I have a total of 0 y's. So just like in this problem where I had 0 y's over here, I have 0 y's over here. I don't even need to mention the y. I know some of you might be thinking of the y to the 0 again, but you don't need to put y's if it's y to the power of 0. We're done right here. And we do have only positive exponents. If this was a negative 3, we might have had to do something like over here, but it's not. We're done. All positive. All right. When we're moving on to number 7, we need to learn a new rule. And we'll review a new rule. You should have already learned this. I'm doing this with red. You need to have this in your notes. This will help you on the final immensely. So this is going to be the power. Okay, I can spell power, Mr. Sindel. There we go. Power rule. Okay, so here's the general rule. I'll do a quick example also. So if I have some base, I don't even need to do an x. I can just say, I'll do an x, whatever. X to the power of a, and I'm going to take all that to the power of b. Okay, what is that equal to? That is equal to x to the power of a times b. I multiply these. Okay, so quick example. Change the blue here. And you can have examples in your notes too if you want, but you don't need to. You definitely need to have this one. That'll help you a lot. So if I have, I don't know, x to the power of -3 and I take that all to the power of 2, what is that going to look like? Well, I just need to multiply this -3 and 2. So I have x to the power of, well, -3 times 2 is -6. So -6, done. That's all you need to do. Just remember that they multiply. So coming back here, just a straight on use of this rule, it's going to be a to the 2 times 3. It's not to the power of 3. Some people might make this mistake of saying it's 8. It's just times. 2 times 3 is 6. A to the power of 6. That 6 can be drawn a little bit better. There it is. A to the power of 6. Done. It's that easy. Okay. Number 8 is a little bit more difficult. So each of these exponents are going to be multiplied by -3. This is kind of like distribution, if you can remember that. Distribution says this -3 is being multiplied by this -4, and it's also being multiplied by that +4. You multiply both of those by -3. So what is that going to look like? I have my x to the power of 4. X to the power of 4 times -3. 4 times -3 is -12. So it's x to the power of -12. Then we're going to deal with the y's. So there's my y. It was to the power of -4. -4 times -3. Well, first of all, a negative times a negative is a positive, so don't need to have a negative here. And then 4 times 3 is a 12, a positive 12. Done. There it is. All right, let's move on to number 9. So we have a fraction here. Let's review another rule. So if I have x to the power of a divided by the same x, the same base, to the power of b, this is equal to x to the power of a minus b. And this is very similar to the last rule. The last rule that we had said if we were multiplying, add. This is the opposite. If we're dividing, the opposite of multiplying, do the opposite. We were adding, now we're subtracting. All right, so that's the rule that you should have written down, but there is another shortcutty way of doing that. But before I talk about the shortcutty way, I want to just review. This should be in our notes, and I should have put this already. Anything, it doesn't even need to be an x, but anything here, anything in the parentheses to the power of 0 is always, always, always equal to 1. And I mean, that's pretty straightforward. So if I have like 100,000 whatever to the power of 0, even though it's big, to the power of 0, bloop, back down to 1. Perfect. So that was our example. All right, so coming back here, I'm going to show you how to do this problem 2 ways. One is using the rule, this rule that we just learned, and the second way is the shortcutting method. And you can ignore the shortcutting method because it might confuse you, and if it does, I apologize, but it is a faster way of solving these problems, and it is mathematically valid. All right, so here's the long way of doing this. First, I say, okay, I have an m to the 0 and an m to the 2 there. So my rule states I'm going to do this number minus this number and write that in the top. So that number minus this number is going to turn into m to the power of 0 minus 2, and I leave that in the top. And then I leave the n to the 3. There's no n up here, so leave n to the power of 3 in the bottom. N to the power of 3 in the bottom. And then that needs to be simplified, right? Because 0 minus 2, I can do that. M to the power of 0 minus 2 is the same thing as m to the power of -2 over n to the power of 3. Don't touch that bottom, it's the same. But there's a problem because if you remember all the way back here, we can only have positive exponents. And this is a negative exponent, which means we have to flip it. And this is coming back to our rule way back, where was it? Way right here. So it's negative exponents, you flip it and make it positive. So I come over here, I'm going to flip this m to the bottom and I'm going to make it positive. So my new answer is there's nothing on the top, so I leave it as a 1. Don't leave it blank, it should be a 1 because what you're really doing is dividing by m to the -2. It's not important, but leave a 1 if there's nothing up there. And it's all going to be divided by, there's our original n cubed that we didn't touch, but this m to the power of -2 is going to come to the bottom, m to the power of +2 now because it flipped and became positive. All right, so that's the long way of doing it. Are you ready for the short way? The short way is find the biggest power of that variable. The biggest power is 2 in this case. Okay, and then you're going to do subtraction from the other direction. So it's m to the 2 minus 0, and then leave it wherever you started. We started in the bottom, leave that answer in the bottom. So I have m to the power of 2 minus 0. And then find the biggest power for n. Well, there's only one, it's just n to the power of 3, and leave that in the bottom, n to the power of 3. This method will let you avoid having to do this flip-floppy rule to get rid of your negative exponents, because if you don't have anything in the top, leave it 1, and then just simplify this. This is 1 over m squared n cubed. So same way to get there, just a little bit faster. If there's a bigger problem, it might save you more time. So both that and this are the same answer, and it is our final answer. Let's talk about number 10. I'm going to do the shortcut method on number 10 to see how this works. So if I don't have any power, this x is to an invisible power. That invisible power is really 1. That's the first step here. Okay, now between the x's, which one of these is bigger, 1 or 0? Well, it's 1, so I'm going to do x to the power of 1 minus 0. So come over here. It's going to be in the bottom. I'm starting in the bottom because 1 is in the bottom, and it's the bigger. So it's going to be x to the power of 1 minus 0. Okay, perfect. Now let's do the y's. Y, this 2 is bigger than this 0, so I'm going to start in the top, y to the power of, and then it's going to be 2 minus 0. 2 minus 0. All right, just making sure we really understand that shortcut works only if you start wherever the biggest exponent is. I started in the top in this one, I started in the bottom for the x. Now let's just simplify. Y to the power of 2 minus 0 is y to the power of 2. X to the power of 1 minus 0 is just x to the power of 1. And x to the power of 1, I mean, this right here will give you full points. But even better is y squared over x. We treat that 1 as an invisible 1, and that is a little bit more mathematically correct. I mean, they're both mathematically correct. This one is just in a better format, I would say. Let's move on to number 11. So number 11, the trick for these is treating these numbers like exponent, or like variables rather. If you do this, whenever you see things with exponents, treat them like variables, and the problem will be a lot more easy. So, or a lot easier rather. So if I come over here and treat this, I'm going to rewrite this problem in terms of x's. That might help us see this better. This is x times x to the power of negative 2. If I treat them like variables, I use the same rule where I'm counting the number of x's. Well, I have an invisible 1 there and a negative 2 there. How many x's do I have? I have a total of 1 minus 2, or negative 1 x's. So this is equal to x to the power of negative 1. Perfect. I'm going to do the same thing, but with 4's, and really I just need to substitute that 4 in for x, and I'm left with 4 to the power of negative 1. Perfect, but again, we have a negative exponent, so we need to get rid of it. And when I don't have a fraction, I need to first make a fraction by making this over 1, and then I flip it. I'm going to switch these two. So 1 is going to be in the top, and then, so this is equal to, and then in the bottom I'm going to be left with 4 to the power of, not negative 1, is now a positive 1. And that just simplifies to 1 over 4, because 4 to the power of 1 is just 4. And there's our final answer, 1 to the power of 4. Or sorry, 1 over 4, 1/4. Let's move on to number 12. Again, treat this like a variable. So it's going to be, how many 3's are there? There's 1 3 there. There's 0 3's there, so a total of 1 3. And 3 to the power of 1, there's 1 3, and that's the same thing as just 3. Anything to the power of 1 is that anything. And maybe that is something worth adding to your note sheet in case you forget that. If I have any variable, x to the power of 1, that's just x. I think that's pretty simple, but if you want to add this, you can. All right, moving on to number 13. So we have simplifying radicals. So let's take some more notes to put in our note sheet for the final. So simplify radicals. That's how I'm going to abbreviate. All right, so essentially what you need to do is you need to separate this into two problems. You need to separate this so that you bring the number over here, all of the numbers, and all of the variables over here. All of the variables. And then there's a separate step for each of these. For the variables, you can cancel out the variables. So if you have the square root of x squared, that will turn into, my equal sign is bad there, is equal to x. And everything else, just leave it as the square root of that. So if you have square root of x, just leave it. If you have the square root of x cubed, just leave it. The only thing that cancels out is the square root of x. For the numbers, this guy is a little bit harder. This is where you have to make a number tree. Or it's called a factor tree rather. Okay, so if you have a factor tree, you'll have a number and then you'll create factors. So I think this one is, we'll just say factor tree, and I'll give you an example of what that looks like. Let's look at the number 45. Let's just do a full-on example actually. So example, this is going to be square root of 45x squared. Okay, so this is going to separate into two parts. One part is square root of 45. The other part is square root of x squared. You are allowed to separate the square roots as long as both of the square roots are still over the numbers. All right, so x squared, oh look, that can be simplified to x, so that turns into an x, perfect. Now we need to do a factor tree for square root of 45. And really you can just do a factor tree for 45. So 45, what times what is 45? Well, I see that, what is this going to be? 9 times 5 is 45, and 9 is 3 times 3. So from here, if you find any doubles, once you have all the factors are 3, 3, and 5. If you have any doubles, I'm going to circle the doubles. Those doubles can be pulled outside of the radical sign. So this pair of 3's is pulled outside and turns into just 1 3, and what's left on the inside, this 5 was not circled, so that still has to be square rooted. So it's 3 square root of 5. And you'll see more examples as I go through those problems as well. And I still have this x to deal with, so this is going to be times x. And if I want to be mathematically proper about this, this x should belong with this 3. Everything that's not a radical is on one side. Everything inside of the radical or the square root is on the other. So it's really 3x square root of 5 would be the answer for that problem. So that's generally how we solve these problems. Let's go and see. Oh my God, this is almost exactly the same as our example. So it's great review. Let's do this problem. So we're going to simplify this by separating into the square root of 45 and the square root of n squared. We have a square root of n squared, so that's immediately going to turn into just n. But the square root of 45, it's going to be the same factors. It's going to be 9 and 5. 9 turns into 3 and 3. We have doubles, 3 and 3. So we're going to pull out a 3. 3 is not going to be under a square root, but the 5, there's no double, so it has to stay inside, unfortunately. It has to stay inside the square root. And then we have this n just by itself. And again, I'm going to put that n next to the 3 just to group things together. So this is now going to be turned into 3n square root of 5. Box my final answer. Moving on to number 14. Again, separate. So I have square root of 18, and I have the square root of n squared. Okay, that was pretty bad handwriting. I can try a little bit better. And again, n squared, we know exactly what that is. That's just n. 18, we have to do factor tree for 18. That's going to be 9 and 2, and 9 is 3 and 3. Again, we have doubles. So the doubles can be pulled outside, no square root, but the square root is around the 2. So square root around the 2. And then multiply by n, and then let's just make everything that's outside of the radical sign on the same side, so the 3 and the n. So this is equal to 3n, and then radical 2, square root of 2. Final answer, box it. Moving on to 15. Same process again. So numbers, square root of 45 on the left, square root of m on the right. Notice that square root of m is not able to be changed. That's kind of one of the things I said. If it's just square root of a letter, just leave it as that letter. So this is just going to be square root of m. We can't change it. Square root of 45. Oh, we know what the square root of 45 is. We've already done that problem. It's 3 radical 5. So whenever you see the same problem, it's just save work. So this is 3 radical 5. 3 radical 5 times radical m. Okay, so we need to group everything together. Everything that's not in a radical, just a 3, is brought out and grouped together, grouped by itself. And then the 5 and the m are grouped together, and that means is they're both underneath the radical symbol. So it's going to be 5m inside of the radical. So it's a square root of 5m. You're allowed to separate them, and you're allowed to combine them over again. And that's the final answer, 3 square root of 5m. All right, for 16, we have square root of 100 pulled out and square root of p. Square root of p can't be done, we can't do anything to it. Square root of 100, oh, square root of 100, that's just 10. And if you don't know that, the factor tree, I could do the full factor tree out. So it's 10 times 10, and 10 is 2 times 5 and 2 times 5. And look, we have a pair of 2's, so bring out a 2. We have a pair of 5's, so bring out a 5 times 5. And nothing is left over. We have nothing inside of the radical. So bring down the square root of p, and we're left with 10 square root of p. 10 square root of p. That's our final answer. Box it. All right, number 17 and 18. These guys take a bit of time, but it's definitely worth diving into to figure out why they work and how to solve them. So the general answer for solving these problems is to make a table. The table is going to look like this. You'll have, I guess we can start up here. So an X and a Y. And the numbers that I like to choose are -2, -1, 0, 1, and 2. And you might be saying to yourself, Mr. Sindel, that is a lot of numbers. I only want to do -1, 0, and 1, or I only want to do 1. Let me tell you that you can do 3, but doing 1 or 2 is probably not going to work. But there is a shortcut to doing these, and I will be showing you with probably number 18 and maybe talking about it in number 17. All right, so the table basically says sub in -2 for x. This x is going to be turned into a -2. And that's going to be using our rule of negative powers. And hopefully you have that in your notes. So that's what I'm going to be using. And I'm going to do that problem right down here. I can do it in black so you don't get confused with the table at all. So I have the equation y equals, I'm just copying down this problem, y equals 1/2, haven't done anything yet, times 3 to the power of, okay, now things are going to change. This x is now going to become a -2 because we're pulling from the table. 3 to the power of -2. We need to figure out this part first before we go on with the rest of the problem. 3 to the power of -2, I need to first make this into a fraction, and then I'm allowed to flip it to get rid of that negative power. So the fraction is now going to become 3 to the -2 over 1. Now I'm allowed to switch the top and the bottom. So I'm going to rewrite this problem. Y is equal to 1/2 times, I haven't changed anything on the left. Now the stuff on the right is going to change. This 1 was on the bottom. Now it's going to be on the top, 1. On the bottom is now going to be 3 to the power of -2, but this is going to change to a +2, so it's going to be 3 to the power of +2. Now 1/2 times 3 to the power of 2, or 1 over 3 to the power of 2. I need to simplify this still a little bit further. This thing is equal to y equals 1/2 times 1 over 3 squared is 9. Now I need to multiply fractions. You multiply straight through, top times top, bottom times bottom. 1 times 1 is 1. 2 times 9 is 18. 1 over 18. Okay, so 1 over 18 is basically 0. It's a really, really small number. I mean, I could do it right here. 1 divided by 18. It's 0.0555 repeating. It's a very, very small number, but close to 0. That's the main part. So I can say right here, 1 over 18. And I know in my head, maybe I should do it in blue. I know in my head that number is basically 0. It's really close to 0. Okay, now what we're going to do is we're going to plug in -1, and we're going to look for a pattern in the table. And if you already know the pattern in the table, and this will be really easy for you. So what I'm going to do is I'm going to plug in -1 and do this work again. And I need more room, so let's go to a new sheet over here. So my equation was y equals 1/2 times 3 to the power of, y equals 1/2 times 3 to the power of, we did -2, let's do -1 now. So again, we need to get rid of this negative power first, so I'm going to make this problem into a fraction. And now I'm allowed to flip the fraction, so it's now going to be 1 over 3 to the power of, it used to be -1, now it's just a +1. And don't forget to rewrite the rest of the equation. Y equals 1/2 times this. 3 to the power of 1 is just 3, and now we can just multiply straight through. 1 times 1 is 1. 2 times 3 is 6. So my answer for that table value is 1/6. 1/6. Okay, I'm seeing some sort of pattern here, maybe dealing with this number. Do you see it yet? Let's go out and do just one more. This one is pretty easy because it's to the power of 0. So this is a new problem, just a little wavy line so your teacher can see you're working on a new problem. Y is equal to 1/2 times 1/3. Sorry, it's not 1/3. I didn't flip it yet. It's 3 to the power of 0. Anything to the power of 0 is 1. Yeah, you're correct. So it's y equals 1/2 times 1. Well, anything times 1 is just whatever you started with, so it's 1/2. So I come back over here. Yep, the table value is 1/2. Do you see the pattern yet? The denominator, the bottom here, is getting smaller by a factor of 3. So 18 divided by 3 is 6. 6 divided by 3 is 2. 2 divided by 3 is 2/3, and then it's going to flip. But that is the pattern so far. Another cool little trick that I would like to mention, and this is just to help you, I'm going to do this in red because this is important and should be in your notes. Whenever you have a 0 for your x value, the number that you get for the y, this value over here, will always, always, always be the number that doesn't have any x attached to it. This has an x attached to it, so don't worry about that. That's how to find the pattern. But this number right here corresponds to what the y-intercept is, where the x value is 0. So that's a way to check our work. Yay, we got it correct. We're checking our work. 1/2 is indeed this y-intercept. And I could keep on going on just with doing this evaluation. And it's pretty straightforward because we don't have any negative powers. So let's go ahead and do that really quick. So I'm going to come over here. Oh, I don't want to use red. I want to use blue. All right, so I'm left with y is equal to 1/2 times 3 to the power of 1. 3 to the power of 1 is just 3. And let's make this over 1 so I can multiply my fractions. 1 times 3 is 3. 2 times 1 is 2. So 3/2 is my table value. I'm going fast, but the video is posted online, so you can come back and look at this if you need to. Doing it for 2, I'll just do it again really quick. So this is y equals, bad equal sign, equals 1/2 times 3 to the power of 2. 3 to the power of 2 is 9, so I'm just going to rewrite this. Y equals 1/2 times 9, and to make sure that I have fractions multiplied by fractions, I'm just going to do 9 over 1. 1 times 9 is 9, 2 times 1 is 2, so 9/2. 9/2. And you should see the pattern. Every single time I'm going down in terms of the table, assuming I'm going from a negative value to a positive value over here, every time I'm going down, I'm multiplying by 3. Multiplying by 3. It's a little bit hard to see with fractions, and I know that. This will still have fractions and it'll be kind of hard, but multiplying by 3. And this multiplying by 3 corresponds to that number right there. You multiply by whatever you have right there. And I could say that again, I guess, just to be consistent. Okay, whew, I know, a lot of work. I'm sorry, but here we go. Now we can finally graph this thing. So x is -2, so I come over 1, 2, and then I go up 1/18, and we said that's basically 0. So I'm just going to graph it at 0. It's really hard to graph that one. -1, -6. Again, this one is really close to 0. It's a little bit above 1/18. So -1 and a little bit above 0. You can barely even notice that it's changed. And then at 0, it's up to 1/2. So at 0, it's halfway in between 0 and 1. And then at 2, it's 9/2. 9/2 is the same thing as 4.5. Oh, wait, I didn't get to 1. Sorry, I skipped 1. Let's come back. 3 divided by 2 is 1.5. So I go 1 up to 1.5. How to get 1.5? I just did the math in my head. You can check 3 divided by 2 using long division or with a calculator. 9 divided by 2 is 4.5, so I go over 2 up 4.5, right about there. Perfect. I have all my points. Let's make those a little bit bigger so that my teacher can see those. It's a good idea. This is where we have to do our best to draw a curvy line that goes through these. Remember that whenever you have an x that's in a power, you're never ever, well, I shouldn't say never ever, you generally, like 99.999% of the time, will never have a straight line. It'll be a curvy line. And this one is indeed a curvy line. The best way to draw a curvy line is to draw a lot of short little dashes that connect up, and then overall it looks like a curvy line. And make sure that you have arrows at the very end to let everyone know that it does go on forever and ever. I just only chose those values to show you. Whew, and we are done with 17. Let's go on to 18. 18, I'm going to use a little bit more of a shortcutting method. This is the original method. Actually, I'm not really going to do the shortcutting method because I feel like that'll confuse too many of us. I'm just going to go ahead and do the same method again, but faster. If I've already been going fast, then you can probably slow down the video or something in the options down in the bottom right. So here we go. Set up our table, x and y. Same values, same exact values, -2, -1, 0, 1, and 2. Subbing in these values, what do we get? So let's move you, actually we can keep you over here. We'll do our math right here. So our equation was y equals 1/4 times 3 to the power of, I'm choosing my x to be -2 in this case. And this is going to change into y equals 1/4, just copying down the problem, times rule of negative power means I'm going to flip it. It was 3 over 1. Now it's 1 over 3 to the power of a +2 now instead of a -2. And then multiply straight through. 1 times 1 is a 1. This is a 3 squared, which is 9. 9 times 4 is 36. That's a very small number. Okay, so it's going to be 1 over 36. That's even smaller than 1/18. And then I just do this over and over again. So it's going to be y equals 1/4. Do a squiggly line so I know I'm on a new problem, times 3 to the power of -1. 3 to the power of -1 is going to turn into 1 over 3 to the power of +1. And then multiply the tops, the numerators. 1 times 1 is 1. Denominators, 4 times 3 is 12. And there it is, 1/12. And we can verify we are going the denominator is going down by a factor of 3, which means the entire number is going up by a factor of 3, up by this factor right here. You guys remember the shortcut for 0? Back over here. The shortcut for 0 says just plug in that number. It's 1/4. Done. All right, and then we have easy numbers. Y equals 1/4, forgot my squiggly line, 1/4 times 3 to the power of 1. And that's the same thing as 3 to the power of 1 over 1. 1 times 3 is 3. Denominator, 4 times 1 is 4, 3/4. Okay, move him. And then new problem, y equals 1/4 times 3 to the power of 2, which is the same thing as 3 to the power of 2 over 1. Just get our fractions. 3 squared is 9. 9 times 1 is 9. 4 times 1 is 4. So this is going to be 9/4. And this makes sense too, because 3/4 times 3 is 9/4. We're multiplying each step to, by 3 to get from one step to the next, times 3, just like we did in the last problem. Time to graph this. -2, 136. This is basically 0 again. So I go -2, basically at 0. Oh my gosh, my computer just kind of lagged there. -2, basically 0. -1, 112, basically 0 again. It's maybe a little bit above, if you can see that. 0, 1/4. 0, 1/4 is right about, it's almost like a straight line. I know, it's not though. This one is still curvy. And then if I go to 1, I go to 3/4. So 3/4 is right about there. And then 2 goes to 9/4. 9/4, 8/4 is 2. So this is a little bit above 2. It's 2.25. So I go 2, and then I go up to 2.25, which is right about there. And you can see it is starting to make this curve. If we went over to 3 and made a new value, we'd see that this is 9 times 3 is 27/4. And 27/4 is almost 7. It's 6.75. It would come all the way up here to 6.75, like right there. But we don't have that value, and I don't expect you to, neither does Miss Anderson. These points are good enough, and do your best to make a curvy line through them. Sound of X. And this line does go flat on forever and ever. If you wanted to know that, make sure you have the arrows to say that they do go on forever and ever. And there's problem 18. And that means we are on to problem 19. So we're adding polynomials. And some really quick notes here for adding polynomials. So I'm just going to say plus polynomes to abbreviate polynomials. Whenever you're adding polynomials, basically you're looking for same powers. If they have the same powers, that means that you are allowed to add them. If not, you can't add them. So if they have the same powers, then add. The other thing, I'll just make this kind of a note that doesn't really need to be in our notes. So just a sub note, I guess. Be careful of distributing negatives. And that is really abbreviated, but basically what I'm saying is if I have some giant polynomial right here and it says minus some giant polynomial over here, this minus sign right there, it needs to be distributed into each of these polynomials before you can start adding them. So be careful when you have a negative there. Let's go ahead and see a quick example, and then we'll jump into the problems for how to do same powers. So if I have 3x squared plus 2x, and I'm going to add this polynomial with, this is an example, I should label this, with, I don't know, something like 3x cubed plus 2x squared. I have to look for things that have the same powers. Powers are this number, this exponent up here. Do I see a power of 2, x to the power of 2 anywhere? Not there, not there. Ah, there. That means that this number 2 and this number 3 can be added, and I don't touch the x squared. The x squared stays there. So 3 plus 2, that's 5. And leave the x squareds. Okay, x to the power of, it's invisible, so it's 1. Do I see any invisibles or 1s? X to the power of 1, x, that's 2, and that's 3, that's 2. Oh, if there's none, it's just that one. So plus 2x to the power of 1. Okay, so we can check these off. Did that one. We end up doing that one. We just have one left, and because there's only one left, it can't be added to anything else, and that's just it. You might want to put it right here, but I know that it's a little bit better form to go in descending power. It goes highest power, next low, or next highest. So the highest power is really 3, so I'm going to write it over here on the left. It doesn't really matter. It's still mathematically correct to write it on the right, but I'm going to put it on the left. 3x cubed plus that, and there's my final answer for that example. Quick example, but let's go into the problems. You'll see them a little bit more in depth. Okay, so we're looking for same powers. N to the power of 3. Do I see any other n's to the powers of 3? That's what I'm looking for. That's n squared. Nope. That's n squared. Nope. That's just a number. There's no more n to the power of 3's. It's just that one. So let's rewrite it. 8n to the power of 3. Done. Next, so I'm going to put a little check mark so I don't accidentally add that one again. N to the power of 2's. Do I see any other n to the power of 2's? So n to the power of 2, oh, there it is, n to the power of 2. That means I'm going to leave the n to the power of 2. I'm going to add the number out in front. That number in front is technically called the coefficient, but it doesn't really matter. Just add those numbers, 2 and 8. 2 plus 8 is 10, so I'm going to say that's 10. And don't change the n squareds. Those stay the same, n squared. Okay, so we just did those two. Well, we're only left with this last one, so I'm just going to rewrite it, -1. And there's our final answer, and it is already in descending power. It goes 3, then 2, then the next highest, done. Number 20. I see a p cubed right here. Are there any other p cubes in the house? P cubed, no. There it is, p cubed. So there's 5 plus 4. I'm allowed to add them now that I've unlocked the fact that they're both p cubes. 5 plus 4 is 9, and then leave the p cubes, p cubed. You only change the power right here when you multiply. Whenever you're adding, there's an adding sign there, adding sign there. Well, that's technically adding a negative. When you're adding and subtracting, these can never change. They are the same. But when they're multiplied, then they can't change. These are all adding, so they always stay the same. So we just did those. Check those off. Okay, 6. Are there any other numbers in the house? There's a 6 there. Oh, yeah, there it is. So 6, and most people, not most people, some people might think that the answer here is 9. 6 and a 3 makes a 9. But you always include the sign in front of it. It's a positive 6 and a negative 3. A positive 6 plus a negative 3 is the same thing as a 6 minus a 3, which is just 3. So the answer here is +3. That is our final answer. Box it, done. Number 21. We're looking for m cubes. Are there any other m cubes in the house? That's an m to the power of 1. So no. That's a 7. No, that's not an m cubed. There's an m cubed. Okay, so I can add that number, the coefficient. 6 plus 2, that's an 8. M cubed. Perfect. Check off those that I just did. M to the power of 1s. Are there any other m to the powers of 1s? Anyone here? No. Oh, there it is. M to the power of 1. So I can add those two together. Any other ones? Nope. Okay, so it's just those two. I have a -4. Remember, I include the negative with it. And, oh, there's nothing in front of that m. Remember, if there's nothing in front of the variable, nothing in front of the letter, you assume that it's 1. So it's -4 and a 1. -4 plus 1 is a -3. So that's going to be a -3m. Perfect. Check off those two. And finally, we have numbers. Remember, we include that negative, so it's a -7 plus a -3. -7 and a -3, they're both going negative, and another negative in the same direction. So you're really having a -10. If they're both going in the same direction, you really are adding them. So it's going to be a -10. Box it. Final answer. Number 22. Last one for this type of problem. We have x's. X to the power of 1s. Are there any other x to the powers of 1s? No. No. There it is. X to the power of 1. So those two I'm going to be adding. No. No. So it's just those two. 4 plus, invisible. Invisible means 1. 1 plus 4 is a 5. 5x to the power of 1. I can just leave it blank. It's fine. Okay, next. X squareds. Are there any other x squareds? I can even do this in a different color. That's a good way of showing this. X squareds. Nope, that's an x to the 4th. Nope, already did that one. I should have checked those off. That's not an x squared. There's an x squared. And it's a -1 x squared. And this is an 8x squared. So an 8 and a -1 makes a 7. So this is +7x squared. Perfect. Check those off. Let's move on to our next. Let's go to black. Next problem. So we have x to the power of 4. Are there any other x to the powers of 4? Remember to include that negative. There it is. A -3x to the power of 4. So it's going to be a -5x to the power of 4 and a -3. So -5 and a -3. Again, these are both going negative and then negative again. So you're really adding these negatives. And it's going to be a -8x to the power of 4. This is not written in descending order. You'll get full points for this. I'm pretty sure. I'm like 99% sure. But just to make it a little bit more mathematically correct, I'm going to move this term with the negative in the first place and then the next highest place. So I'm kind of just reversing all these. So my answer is -8x to the power of 4 plus 7x squared And there's no sign in front of this, which means it's a positive, so it's a positive 5x. Box it, final answer. I just wrote it in descending order. It makes it look a little bit more nice in terms of math. All right, for these last 3 problems in the video, I know I probably could have gone to 26 because it's the last one in this set, but I'm only going to go through these 3. This is the one that I have to be careful about because it's a subtraction. I need to distribute that subtraction sign before I can even continue with this problem. So I'm going to rewrite this problem right from the get-go. As soon as I see that these 2 are separated by a subtraction sign, I'm going to distribute. This negative sign is going to be multiplied by this one and by this one. So my new problem, I don't really want to rewrite that first one, but I mean, you can if you want. This is going to be 5m cubed minus 1, and now it's going to be plus, because I distribute the negative, there's no longer a negative, and it's going to be this new thing in parentheses, this new polynomial is a negative 2m cubed, negative 2m cubed. That's a weird 3. Try again. Better. And then a negative times a negative 4 is a positive 4, so positive 4. And I guess I can just write this to make it look nice, 5m cubed minus 1. Now, it's the same problem as we had over here, just with a plus sign in between. So let's go ahead and do that. So looking for all the m cubes, there's an m cubed there, 5 and a negative 2 makes a 3, and then just leave the m cubes. Again, you never change the m cubes when you're adding. Okay, next, we're looking for something else. So we can check off those 2. We see a negative 1 here, include the sign, and a positive 4 here. So a negative 1 and a positive 4 makes a positive 3, plus 3, done, box it. Once you have check marks above each of these terms, then you're done. All right, again, we have a negative. Go ahead and distribute this negative into each of these terms. So I'm not going to rewrite this time, it'll go faster. So this is now turned into a positive, it makes it easier, times a negative 7m cubed, and this is a negative times a negative, so it's a positive 8m cubed. So positive 8m cubed. All right, so let's go through and find all the m cubes. There's an m cubed there, and oh, Mr. Snell made a mistake here. Let's undo a few times. This is supposed to be m to the 4th. Thank you for catching that if you called that out or saw it in your mind and didn't say anything. But yes, it's supposed to be m to the power 4 there. Okay, so m cubed there and there. Great. So it's a 5 and a negative 7. That makes a negative 2. Negative 2m cubed. Next. Yes, we should check this off too. Next, we have m squared. So I have an m squared there. No more m squareds. If that's the only one, just rewrite it. So it's plus 2m squared. All right, just moving down the line. Okay, so we have a check mark there, check mark there. The only one there is this m to the 4, and it's the last term, so just rewrite it. 8m to the 4. There's no other m to the 4s if that's the last term, right? And I'm going to rearrange this again because I like having them in descending order where this highest power is first. So I'm going to just move this guy right there. So my final answer, in fact, I could just go like this. I have technology, 8m to the 4th, and then I can use my little erasing tool. Whoa, that's a big eraser. Like that, there. And my final answer is going to be boxed. Last problem for this video. So I have a negative sign. I need to distribute that negative into all 3 of these terms. So I'm going to rewrite this second term. It's going to be plus, and then here we go. Negative times 1 is a negative 1. Negative times a positive 2r cubed is a negative 2r cubed. A negative times a 4r to the 4th is a negative 4r to the 4th. Okay, and then I'm just going to go through with my normal process. So all the r's with invisible powers, oh, that's the only one, so just leave it. R, check it off. Next color, next term. R to the power of 3, r to the power of 3, nope, oh, there it is, r to the power of 3, so I'm left, and remember, it's including that negative sign. So it's a negative 2r to the power of 3 and a 5r to the power of 3. 5 and a negative 2 makes a 3, so it's going to be plus 3r to the power of 3. Check those off. All right, next color. We have a 1. Any other just numbers? Oh, there's just a number right there. It's a 1 minus 1. 1 minus 1 is 0, so don't write it. Check those off. There's nothing there. You could write plus 0 if you wanted to be, I don't know, extra meticulous, but you don't need to. It's just eliminate it. And we have checked off all of them except for this last one, so just check it off and just rewrite it. And again, we could write it here, negative 4r to the power of 4, but to have it in descending order, this negative 4r to the power of 4, I'm going to move that in front right here. So let's undo that, and it's going to be in, well, actually, hold on, negative 4r to the power of 4, because I need to rearrange this whole thing. I thought I could just put it there and be done, but this one needs to be moved as well. So let's rewrite this whole term. So it's going to be a negative 4r to the power of 4, then do the red, plus 3r cubed, and then the blue, plus r, done, box it. All right, that concludes this video. Thank you for watching.